Hello everyone and welcome to our presentation on advection. Advection by definition is the transport of properties by the wind. And actually convection is vertical transport, but here we're talking about horizontal transport. Horizontal transport meaning over the horizon. When we talk about convection, we look at the vertical transport, and usually meteorologists, when they talk about convection, they're implying thunderstorms and thermals and things like that. But this is the horizontal transport of properties by the wind. And what can be transported? Just about anything. In the previous picture, you saw dust being transported by the wind, but it can also be temperature, moisture, some other esoteric stuff like momentum can be transported or advected, but just about any meteorological property. So what we're going to do is we're going to look at different reference frames, and this is kind of difficult. We talked about this before. It's kind of confusing, the Eulerian versus Lagrangian. If you got that down, then this shouldn't be too bad. But Eulerian is just at a given location looking at changes over time. You're not moving in any direction. You're just standing in one location, and you're seeing how things change around you. So that's your local derivative. If you had some property A, you can see how A changes with time without moving around anywhere. But the Lagrangian reference frame is moving along with the air and then seeing how the wind changes as you move with the air. So that would be the total derivative, and that's your dA dt on the left side. So here's our equation for the total derivative, dA dt, the total derivative, or the Lagrangian reference frame, is equal to dA dt, the small deltas, which imply a local change. And that's your Eulerian, plus dA dx dx dt, which I put in a red box, plus dA dy dy dt. So I put the dy dt in the red boxes. Everything to the right of that plus sign has to do with motion and also gradient. So we're going to put boxes around the dx dt and the dy dt, and you guys probably remember that dx dt is motion in the x direction, which we call u, and dy dt is motion in the y direction, a change in the y position with time, and we're going to call that v. So that is our horizontal wind vector, dx dt plus dy dt, and that gives us the total horizontal wind component. We're going to call that big V. We'll put a vector on that. So looking at our next equation, it says V, the vector V, wind vector field, now this is a horizontal wind, is equal to U plus V. And we have unit components I and J, vector components. So that kind of makes things a little bit simpler. We don't have to write this dx dt and dy dt every time. Instead, we just write u and v. So our Lagrangian reference frame, our total change, our total derivative following a parcel, dA dt, is your local, and that's the small dA dt, plus this motion, u and v, but they're multiplied by the change in some property A in the x direction and some property y, some property A in the y direction. So remember, I don't know if you've watched the presentation on gradients, but change in some property in the x and the change in some property in the y is your horizontal gradient. And since we're looking at some property A, could be temperature, pressure, whatever, we're going to call it A, we can use the symbology for gradients, and some places you'll see it called grad A, other places you'll see the del operator, and you'll see del A. So we'll stick that in together with the wind vector V, which represents U and V wind vectors, and we use the dot product So now our equation looks really simple. It looked really complex before, now it looks really simple. And what this says, the equation on the bottom says that the change in A with time following a parcel of air, Lagrangian reference frame, is equal to the local change plus a change that results from motion and also from gradient. So that's V dot del A, or the wind vector, the horizontal wind, dotted with the gradient of A. So what we're going to do now in advection, we are going to assume that as we follow along with the parcel of air, we don't see any changes in that parcel of air. I know that doesn't always happen, but sometimes the changes are really small or they're really insignificant. So we're going to assume that following the parcel, there's no changes, and as the wind blows along, A doesn't change in that parcel. So if that's the case, that means that the left-hand side is 0, and we can rearrange that algebraically so that we have the local change in some property A is a function of V dot del A. Oh, there's a minus sign in front, and that minus sign is important. But that is the advective term. So that's the advection of some property A. So you can actually figure out at a given location how things are going to change if you know the gradient and also the strength of the wind. In other words, the advection. So this is what happens. You get a local change as a result of the wind moving through. You guys probably know this already. When the wind blows out of the north, it gets cold. That's advection, cold air advection. When it blows from the south, that's warm air advection. There's a gradient in temperature, and there's some wind. And those two things together cause local changes. So what you need for advection is wind and gradient, as I implied. And here's the example of cold air advection, cold air coming out of Canada. There's the gradient. It's colder up north, it's warmer down south, and the wind's blowing from the north to the south. That's cold air advection or negative advection. Warm air advection is just the opposite, where you have the wind blowing from the south. Same gradient, wind blowing from the south, though, across this gradient, bringing in warmer temperatures to the north. So the magnitude of advection is a function of three things. Number one, it depends upon the strength or the magnitude of the wind. Number two, the strength or magnitude of the gradient, whatever gradient you're looking at, temperature, pressure, whatever. And number three, the angle between those two, between the wind and also the gradient, between those two things. And that's an angle that will be less than 90 degrees. Less than 180 degrees. So let's look at each one of these and see how it affects advection. So here's an example where you've got a gradient, a temperature gradient, with colder air to the north, warmer air to the south. You've got, and that's the arrow for gradient pointing to the south. Remember, gradients always point to higher values and point 9 degrees to the isoplus. That's the gradient. And here in this case, we've got wind. And we've got a weaker wind on the left, a stronger wind on the right. The one on the right will have stronger advection, and the one on the left will have weaker temperature advection. Here's an example, another case, where you have the same wind and also the same direction and the same speed. They're both 20 knots moving to the south, but the gradient is different. The gradient is pointing to the south, but you have a weaker gradient. In other words, the temperature doesn't change as much over a given distance on the left, but a much stronger gradient on the right, where the gradient or the change in temperature is very rapid over a short distance. So you have a stronger gradient, and it implies a stronger advection on the right side than on the left side. And then finally here we've got the temperature gradient that's the same every way. The strength of the wind is 20 knots everywhere, but we're changing the angle. And you can see that on the left, since the wind is blowing parallel with the isoplus, there's no advection. But as you increase the angle between the isoplus and the wind, you notice that the advection gets stronger and stronger until it's 90 degrees. And when you have an angle between the isoplus and the wind of 90 degrees, or in other words, the gradient is pointing more or less the same direction as the wind, then you have your strongest advection. So advection is extremely important because it helps us understand what's going on in the atmosphere. It helps us kind of visualize where we're going to see stabilization and destabilization. We talked about that already in the changes of stability. Remember, cold air advection aloft and warm air advection aloft and things like that. But also, this is what actually makes weather systems move, and also weather systems intensify. We'll talk about that later on at the end of the semester. So to figure out advection, you need to know the magnitude of the wind, how strong the wind is, and the magnitude of the gradient, and the angle between those two. Okay, so what we're doing is we're going to actually calculate the dot product. And the dot product is a kind of a multiplication between two vectors. And it requires that you know the angle between those two vectors. So that's what the cosine theta is. And then the v is the velocity of the wind, in other words, the magnitude of the wind. And then also grad t is the gradient. In this case, we're looking at temperature gradient. Something that's really important is the minus sign. And we don't want to lose that. If you lose that, that changes the whole equation. So make sure we keep track of that minus sign. So those three things together, the magnitude of the velocity of the wind, the magnitude of the gradient, temperature gradient in this case, and the angle between those two will cause or will result in a change. In this case, we're looking at a change in temperature over time. And that's what the on the left side, that delta T over delta T is. Delta big T, delta little t. So local change, that's your local change in temperature with time. So let's look at three cases in calculating advection. In this case, temperature advection, we're looking at where the angle is less than 90 degrees, where the angle will be equal to 90, and where it's greater than. So here we are. We're looking at the gradient pointing to the southeast, and the wind is blowing straight out of the north to the south. So the angle between those two is less than 90 degrees. It looks like it's about 40 or 45 degrees here. The gradient increases to the south, higher values to the south, lower values to the north, temperature gradient. I guess actually northwest is the lower values. So looking at this, I intuitively know that the wind is blowing from cold to warm, so it should be cold air advection. Let's see if the numbers work out. Now the angle between the gradient and the wind is less than 90 degrees, and if you calculate any value less than 90 degrees, it'll give you a positive value for the cosine. And remember that you had a minus sign out in front of that equation. So if this is positive and that whole right side is positive, you throw a minus sign in front of it, that makes it negative. So that means your left-hand side will be negative, which means that we'll have a decrease in temperature with time. And that's what we would normally expect. If you wouldn't expect the wind to blow out of the north with colder air to the north, you got cold air advection. So that means that the temperature decreases with time. Local temperature change decreases with time. If the wind is blowing exactly parallel to the isoplus, temperature lines, isotherms, in this case, it's not blowing warm to cold or cold to warm, it's just blowing parallel. So if that's the case, if you take the cosine of 90, that gives you 0. And that tells you that whole right side is 0, which means your left side is 0. So the change in temperature with time is 0. There is no advection. In this case, no temperature advection. Now let's take a look at a case where the wind is blowing from the south to the north, from warm to cold, actually kind of southeast to northwest. The angle between the wind and the temperature gradient is big. It's more than 90 degrees. And if you do the math, if you stick in a number that's more than 90 degrees, between 90 and 180 degrees, you'll get a negative cosine. And remember that the right-hand side had a minus sign in that equation. So a minus times a minus is a plus. That means the left-hand side of that equation, which is the change in temperature with time, that'll be plus also, meaning that temperature is increasing at a given location, local. And that makes sense. If the wind's coming out of the south, temperature should increase with time. So you could use advection. We were doing advection. You can use this for temperature, but you can use it for moisture. You could do it for a lot of different things. All you need to do is figure out the gradient and then look at the wind and which way the wind is blowing. Here's an example of advection, temperature advection. We've got 3 different points, A, B, and C, and they're located 3 different places, winds blowing differently at each location. One type of temperature advection is occurring at these 3 different locations. At point A, the wind is blowing from cold air to warmer air across the gradient, almost at a 90-degree angle, so there's strong colder advection at point A. At point B, you can see the lines, the isotherms, are pretty much parallel to the wind. The wind might just slightly be across it, but really there's not much advection going on there if the wind is not blowing across the gradient. And then at point C, the wind is blowing from warmer temperatures to colder temperatures across the gradient, and you can see there's strong warm air advection at point C. Here is an 850 millibar map with dew points, and the dew points are indicated by the green. And looking at that, you can see that there is different types of moisture advection. At point A, the wind is blowing from drier air to more moist air. It's going across those green lines from where there is very little moisture to an area where there's much more moisture, so that's dry air advection. At point B, the wind is blowing from areas that have higher dew points to areas that have lower dew points, and that's moist air advection. And then finally at point C, you can see the lines of dew point, what we call isodrosotherms, are parallel to the wind, so there's no temperature advection at point C. So those are a few examples of how to determine if there is advection, what type of advection is occurring over a given area. I hope you enjoyed this presentation.